Now, in this lecture, I will discuss hybridization and the band theory. After studying this lecture, you shall be able to know what the concept of the hybridization, understand the concept of redistribution of energies in hybridization, know about how hybridization indicates the shape of the molecule, and understand the metallic bond and the concept of the band theory. Now, we will discuss first what is hybridization. The phenomena of mixing up atomic orbitals of similar energies so that a redistribution of energy takes place between them, resulting in the formation of new orbitals of equal energies and identical shapes, is known as hybridization. The new orbitals thus formed are known as hybrid orbitals. The main points of the concept of hybridization are as follows. Number 1. Hybridization involves the orbit of similar energies belonging to the same atom or ion. Number 2. The number of hybrid orbitals produced is equal to the number of orbitals that participate in hybridization process. Number 3. It involves both half-filled as well as completely filled orbitals. Number 4. Type of hybridization indicates the shape of the molecule. Now, we discuss types of hybridization. There are 6 types of the hybridization. Number 1, sp hybridization. Number 2, sp2 hybridization. Number 3, sp3 hybridization. Number 4, sp3 dehybridization. Number 5, sp3d2 hybridization. And number 6 is dsp2 hybridization. Now, let us discuss all these hybridization in detail with a suitable example. First, we take sp hybridization. It involves the mixing of one s orbital and one p orbital to produce two new hybrid orbitals. In sp hybridization, the bond angle is 180 degree and the shape of the molecule is linear. Beryllium fluoride and beryllium chloride are the example of sp hybridization. Let us consider example of beryllium chloride. The electronic configuration of beryllium is 1s2 and 2s2. This is the ground state of beryllium. Since the 2s2 orbital is fully paired, then the fully paired orbitals are not participate in bonding. So, in excited state, the 2s orbital have one electron and the one electron of 2s is shifted towards the 2p orbital. So, a hybrid orbitals are formed, that is sp hybridization, which is linear in shape having 180-degree angle. Next is sp2 hybridization. It involves the mixing of one s orbital and 2p orbital to produce the three new hybrid orbitals. In sp2 hybridization, bond angle is 120 degree and the shape of the molecule is planar triangular. BCl3 and BF3 are the examples of the sp2 hybridization. Now, let us consider the example of boron fluoride. The ground state of the boron is 1s2, 2s2 and 2p1. In the excited state, the configuration is 1s2, 2s1 and 2p2. Now, three new hybrid orbitals are formed, which forms sp2 hybridization. Due to this, the structure is planar triangular shape having 120-degree angle. Next, we discuss sp3 hybridization. It involves the mixing of one s orbital and 3p orbital to produce four new hybrid orbitals. In this type of hybridization, there are three possibilities. Number 1, when the hybridization involves 4 bond pairs only. In this type of sp3 hybridization, the bond angle is 109 degree 28 minutes and the shape of the molecule is tetrahedral. Methane and carbon tetrachloride are the example of sp3 hybridization. Now, let us see that example of methane. The electronic configuration of carbon is 1s2, 2s2 and 2p2. The excited state of the carbon is 1s2, 2s1, 2p3. Because the s or 2s orbital is completely filled, so one of the electron is excited towards the 2p. Due to this, the formation of 4 new hybrid orbitals, which is called sp3 hybridization. The next condition of sp3 hybridization is when the hybridization involves 3 bond pairs and 1 lone pair. In this type of sp3 hybridization, bond angle is 107 degree and the shape of the molecule is pyramidal. Now, let us consider example of ammonia. The electronic configuration of nitrogen is 1s2, 2s2 and 2p3. This is the ground state of the nitrogen. When we involve the 2s orbital and the 2p3 orbital, then the new orbital is called sp3 hybridization, which is pyramidal in shape due to the lone pair of electrons in nitrogen. Next condition of sp3 hybridization is when the hybridization involves 2 bond pairs and 2 lone pairs. In this type of sp3 hybridization, bond angle is 104.5 degree and the shape of the molecule is V-shaped. For example, water. The electronic configuration of oxygen is 1s2, 2s2 and 2p4. So, in this hybridization, one 2s orbital and 2p orbitals are combined, they form sp3 hybridization. In this sp3d hybridization, it involves the mixing of one s orbital, 3p orbital and one d orbital to produce 5 new hybrid orbitals. In sp3d hybridization, the bond angle is 120 degree at equator and 90 degree at axial and shape of the molecule is trigonal bipyramid. Let us see the example of PCl5. The electronic configuration of the phosphorus is 3s2, 3p3. This is the ground state. Now, in excited state, one of the electron of 3s orbitals are excited into the 3d orbital and the formation of 5 orbitals is called sp3d hybridization. In sp3d2 hybridization, it involves the mixing of one s orbital, 3p orbitals and 2d orbitals to produce 6 new hybrid orbitals. In sp3d2 hybridization, the bond angle is 90 degree and the shape of the molecule is octahedral. For example, SF6, the electronic configuration of sulfur is 3s2 and 3p4, which is the ground state of the sulfur. In excited state, one of the electrons in 3s orbital is excited to 3d orbital. So, the formation of 6 new orbitals, that is sp3d2 hybridization formed. In dsp2 hybridization, the square planar coordination compound results from dsp2 hybridization involving mixing of 1s, 1d and 2p orbitals. For example, the complex ion nickel cyanide involves dsp2 hybridization In this case, the oxidation state of nickel is +2. So, the outer electronic configuration of nickel 2 plus is 3d8, which is shown by the diagram. Now, we discuss metallic bond. The force which holds the atoms so closely together in metal crystal is called metallic bonding. They are the theory to explain the nature of metallic bond and the properties of the metal, that is molecular orbital or band theory. Band theory, it is the quantum mechanical treatment of metallic crystal. According to this theory, electrons in the metal are covered the whole crystal lattice and are not localized between two atoms. So, metallic bonding is formed by the delocalization of all the orbitals containing free electrons, and it is similar to molecular orbital theory of covalent molecules. When the two atomic orbitals combine together, two molecular orbitals are formed in which one is bonding and another is anti-bonding molecular orbital. Similarly, when the three atomic orbitals are combined, three molecular orbitals are formed in which one is bonding, second is anti-bonding, and third is non-bonding molecular orbital are formed. Similarly, when the nth atomic orbitals combine, nth molecular orbitals are formed. In case of metallic crystal, nth is the order of 10 to the power 23. Now, let us take an example of lithium metal to explain the bonding in metals. Lithium, having the electronic configuration is 2s2 and 2s1. When the two lithium atoms combine to form two types of molecular orbital, one is bonding, another is anti-bonding. In the outermost orbital, there is only one electron, so all the electrons is filled in bonding molecular orbital. When the three lithium atoms combine, three types of the molecular orbitals, bonding, anti-bonding, non-bonding molecular orbital is formed. When the four lithium atoms combine, four types of molecular orbital in which two are bonding and another two are anti-bonding molecular orbital formed. Similarly, when the nth type of the lithium atoms combine, nth type of the molecular orbitals is formed. Therefore, 10 to the power 23 molecular orbitals are formed, and these are so closely spaced then they form a continuous energy band. In this continuous energy band, there are two types of the bands are formed. One is valence band and another is conduction band. On the basis of valence and conduction band, we have to discuss the properties of conductor, semiconductor and insulators. Conductors, there is no band gap between the valence band and the conduction band. Therefore, a large number of electrons may jump from valence band to conduction band and more conductivity observed. In semiconductor, band gap between the valence and conduction band is small, that is 1 electron volt, and therefore the sum of the electron may jump from valence to conduction band and some conductivity is observed. In insulator, the band gap is too high and therefore none of the electrons may jump from valence band to conduction band and no conductivity observed. On the basis of our presentation, these are the some practice questions, that is, define the term hybridization, explain types of hybridization with suitable examples, explain the band theory of solids with suitable example, explain conductor, insulator and semiconductor with suitable diagram, and write a short notes on sp3, sp3d and sp3d2 hybrid orbitals. These are the references which is used in our PPT. Thank you.